This chapter discusses the different ways that the WWC may calculate effect sizes for individual level assignment studies with continuous measures. For continuous measures, or variables that have many possible values, such as standardized achievement test scores, the WWC calculates a standardized mean difference effect size. The standardized mean difference effect size, or Hedges G, represents the impact of the intervention in standard deviation units. This Hedges G effect size can be conceptualized as roughly equivalent to the Cohen's d effect size, which likely is familiar to many researchers and which represents the average difference between an intervention and comparison condition in a standardized way. Because the effect size provides a common, standardized scale for measuring impacts, it can be used to compare findings across different outcome measures. For the same reason, the effect size allows the WWC to aggregate impacts across outcomes and studies to summarize evidence. This slide shows a general formula the WWC uses to calculate a Hedges G effect size. Hedges G represents the difference between the average of a characteristic for intervention group members and the average of a characteristic for comparison group members, divided by the pooled standard deviation of that characteristic, where the pooled standard deviation is just the weighted average of each group's standard deviation. Where Hedges G deviates slightly from the popular Cohen's d effect size is that Hedges G also includes an adjustment factor for small sample sizes, the omega next to the impact estimate. In order to calculate a Hedges G effect size, reviewers then will need 3 different types of information in order for the WWC to be able to calculate an effect size. First, reviewers will need some estimate for B, which is the unstandardized mean difference estimate for the intervention and comparison groups. This simply could be the difference between the two groups at post-test for some group designs. However, for this unstandardized mean difference, the WWC always prefers covariate-adjusted estimates that control for baseline differences. As we have discussed, covariate-adjusted estimates often are more precise and have less bias than unadjusted mean differences. In practice, these covariate-adjusted estimates are likely to be an estimate from a statistical model, such as a regression or an analysis of covariance. The second type of information needed to calculate this effect size is standard deviations on the outcome measure, separately for the intervention and comparison groups. These are SDI and SDC in the equation. It is important to note that the standard deviations used to compute Hedges G always should be based on unadjusted statistics, which ensures comparability of effect sizes across studies. However, the WWC will accept standard deviations for an outcome measure from national, state, or district norms if an unadjusted standard deviation from the analytic sample is not available. The third and final type of information needed to calculate this effect size are sample sizes, separately for the intervention and comparison groups. These are NI and NC in the equation. To summarize, the most straightforward calculation of a Hedges G effect size from an individual level assignment study for a continuous measure will require reviewers to specify the unstandardized mean difference value, standard deviations by group, and sample sizes by group. Sometimes the WWC has to use test statistics to calculate effect sizes instead of the impact estimate. A study could conduct a covariate-adjusted analysis, such as multiple regression, but still not report sufficient information to compute an effect size using the formulas we just discussed. For example, the study authors might not report the unadjusted standard deviations for the intervention and comparison groups. In such cases, the WWC instead can compute the Hedges G effect size using a covariate-adjusted t-test or F statistic using the following formulas. The formulas each include the t-test or F statistic, the small sample adjustment term, omega, and the sample sizes in each group. The versions involving the adjusted comparisons on the left also include the multiple correlation R squared. So when reviewers are calculating a Hedges G effect size and its standard error using test statistics for covariate-adjusted mean comparisons, reviewers typically already will have separate sample sizes for the intervention and comparison groups, but they will need some additional information beyond what we have discussed already. First, reviewers will need the test statistic value. So either the t-test or f-test statistic for covariate-adjusted mean differences between the two groups. These are shown as t and f in the equations. To calculate effect sizes from adjusted comparisons, the second piece of information needed is the multiple correlation coefficient between the covariates and outcomes. And finally, for t-tests only, if the study authors do not report the t-statistic value, but instead report an exact two-tailed p-value, then the WWC will convert the p-value to a t-statistic following the guidance in Appendix E of the handbook. Now, even when the typical impact estimates are available to calculate Hedges G, reviewers may not have the unadjusted standard deviations for the intervention and comparison group required to calculate the typical pooled standard deviation, which often is used as the denominator in the effect size formula. If this occurs, the WWC does have several alternative methods that can be used for calculating the pooled standard deviation from other types of commonly reported statistical information. The first alternative method can be used if a study reports the total standard deviation for the outcome measure, but does not report the standard deviation separately for the intervention and comparison groups. The total standard deviation can be used to calculate the pooled within group standard deviation if the authors also report the sample sizes for the intervention and comparison groups. The WWC also may calculate the pooled standard deviation from standardized z-scores. Study authors might standardize the response scale of their outcome measures by subtracting the grand mean and dividing by the total unadjusted standard deviation. This generates what often are called z-scores. The pooled standard deviation then can be calculated by assuming that the standard deviation is equal to 1 using the full sample standard deviation approach. The WWC also can calculate effect sizes from standardized regression coefficients, which are sometimes called beta weights in the literature. If study authors report these standardized regression coefficients, then the WWC can calculate the effect size using an alternative formula and the sample sizes by group. Another common scenario is for study authors to report gain score standard deviations rather than post-test standard deviations for the two groups. Recall that gain scores are calculated as the post-test value minus the pre-test value. Some study authors may only report the means and standard deviations for the gain score, but gain score standard deviations are typically smaller than the unadjusted post-test standard deviations, inflating the effect size. If the study authors report the baseline outcome correlation, the WWC will calculate the pooled standard deviation using the gain score standard deviation. This conversion approximates the pooled standard deviation of the post-test scores. Note that the WWC will not apply this conversion if the study did not report the baseline outcome correlation. The WWC also will not report effect sizes based on unconverted gain score standard deviations because they lack comparability with other WWC effect sizes. In some scenarios, a study only may report the standard error for group means but not report the standard deviations separately by group. For unadjusted analyses, only the standard errors of the group means are required. But for covariate-adjusted analyses, the standard errors also require the R-squared for the model. Other studies may not report the pooled standard deviation at the post-test, but instead may report the baseline standard deviations for the intervention and comparison groups. In this scenario, the WWC will allow review team leadership to use baseline standard deviations in place of outcome standard deviations, but only if the outcome standard deviations are missing in the study report and the baseline and outcome measures are the same and use the same scoring procedures. Finally, other studies may not report the total standard deviation, but instead may report the standard deviation from a single group, either the intervention group or the comparison group. In this scenario, the WWC can calculate the Hedges G effect size using the single group standard deviation in the denominator of the effect size calculation. When calculating Hedges G for unadjusted means, if a reviewer has sufficient information to calculate the effect size, they will also have sufficient information for calculating the standard error. This is not true of the covariate-adjusted Hedges G. This is the formula for calculating the Hedges G standard error when calculated using covariate-adjusted mean differences. The standard error can be calculated by multiplying the small sample adjustment term, omega, by the square root of two terms. In the left-hand term under the radical, the standard error of the regression coefficient is divided by the pooled standard deviation, putting the standard error of the regression coefficient on the scale of the pooled standard deviation. And the right-hand term reflects the uncertainty introduced by using the estimated pooled standard deviation in the effect size computation. So, when reviewers are calculating a Hedges G effect size and its standard error using covariate-adjusted mean differences, they will need one additional piece of information beyond what is needed to calculate the effect size, the standard error of the unstandardized regression coefficient. This is shown as SEB in the equation. Sometimes a study may not report sufficient information about the standard error of the unstandardized regression coefficient. If that is the case, the WWC can estimate that value from other types of commonly reported information. If study authors do not report the standard error of the regression coefficient, but instead report the t-statistic for the unstandardized regression coefficient, then the WWC can calculate the standard error as B, the unstandardized regression coefficient divided by t. Studies using analysis of covariance, or ANCOVA, also may report the intervention mean standard error, or SEYI, and the comparison mean standard error, shown here as SEYC. If this is the case, the WWC can calculate the standard error of the mean difference as shown here. But in other cases, a study may not report the information needed to use that formula. If the study authors report the multiple correlations between the covariates and the outcome, or R-squared, then the covariate-adjusted standard error for the effect sizes instead can be calculated using this formula. The WWC always will prefer adjusted R-squared values that account for the number of entered predictors and correct for overconfidence in the model predictions. And if a study reports a negative adjusted R-squared value, the WWC will treat that value as 0%. If an adjusted R-squared value is not available, then the WWC can use unadjusted R-squared values. And if the unstandardized standard error and R-squared value are both unavailable from a study, the WWC will take a cautious approach to calculating the effect size, standard error, and assume a value of 0% for R-squared. This cautious approach will overestimate the magnitude of the standard error, but protect against type 1 error. In the next chapter of this module, we will discuss effect sizes for cluster-level assignment studies with continuous outcome measures.